Beneath the icy crusts of distant moons, hidden oceans could be cradling life as we know it, or perhaps something entirely alien. Europa, one of Jupiter's moons, and Enceladus, a tiny moon of Saturn, are not just frozen rocks in space. They're ocean worlds, with vast subsurface seas that might be teeming with life. Scientists are on the brink of uncovering their secrets, and what they find could rewrite everything we know about life in the universe. So, let's dive in and explore these icy mysteries, where the hunt for extraterrestrial life is as thrilling as it gets. The enigmatic allure of ice-covered oceans. Beneath the icy crusts of distant moons, oceans of liquid water might be hiding, tantalizing scientists with the possibility of extraterrestrial life. These ice-covered oceans, like the one suspected to exist on Jupiter's moon Europa, present a unique and captivating enigma. The ice shell acts as a protective barrier, shielding the subsurface ocean from harmful radiation and preserving its potential habitability. This hidden ocean could be in direct contact with a rocky seafloor, providing essential minerals and energy sources for life. The combination of liquid water, chemical energy, and stability makes these environments compelling candidates in the search for life beyond Earth. The study of subsurface oceans is a thrilling frontier in planetary science. Scientists use a variety of methods to investigate these hidden worlds, including remote sensing, theoretical modeling, and laboratory experiments. For instance, data from the Galileo spacecraft and the Hubble Space Telescope have provided compelling evidence for a subsurface ocean on Europa. These observations include measurements of Jupiter's magnetic field being disrupted near Europa, suggesting the presence of a conductive layer, likely a salty ocean, beneath the ice. Additionally, plumes of water vapor erupting from Europa's surface hint at the exchange of material between the subsurface ocean and the exterior environment. Understanding the dynamics of these icy moons is crucial for assessing their habitability. The thickness of the ice shell, the composition of the ocean, and the presence of tidal heating all play significant roles in determining whether life could exist. Europa, for example, experiences tidal forces from Jupiter's gravity, which generate heat and keep the subsurface ocean liquid. This heat could drive hydrothermal vents on the seafloor, similar to those found in Earth's oceans, which support diverse ecosystems. The chemical interactions between the rocky core and the ocean could also create the necessary ingredients for life, such as organic molecules and energy sources. Exploring these ice-covered oceans presents immense challenges, but also incredible opportunities. Future missions, like NASA's Europa Clipper, aim to study these moons in greater detail, using advanced instruments to analyze their surfaces and subsurface environments. By understanding the conditions and processes at play, scientists hope to uncover the secrets of these enigmatic worlds and perhaps even find evidence of life beyond Earth. The allure of ice-covered oceans lies not just in their potential to harbor life, but also in the profound questions they raise about the nature of life itself and our place in the universe. Beneath the frozen veil, a realm of mystery. Beneath the icy crusts of certain moons in our solar system, a tantalizing possibility emerges: subsurface oceans that could harbor life. These hidden seas, shielded from the harsh radiation and extreme temperatures of space, are among the most promising candidates for extraterrestrial life. Europa, one of Jupiter's moons, is a prime example. It is believed to have a global ocean beneath its icy surface, kept liquid by tidal heating from Jupiter's gravitational pull. This ocean could be up to 100 kilometers deep, making it a compelling target for astrobiologists. The science behind these subsurface oceans is fascinating. On Europa, the ice shell is thought to be in constant motion, with new ice forming at the base and older ice being pushed up and out at the surface. This process could allow for the exchange of materials between the ocean and the surface, potentially providing nutrients and energy sources for life. Additionally, hydrothermal vents on the ocean floor could create localized habitats similar to those found in Earth's oceans, where diverse ecosystems thrive. Exploring these icy moons presents significant challenges. The thick ice shells make direct access to the subsurface oceans difficult. However, missions like NASA's Europa Clipper, set to launch in the near future, aim to study the moon's ice shell, composition, and geology in detail. These missions will help scientists understand the potential habitability of Europa's ocean and pave the way for future exploration. The search for life beneath the frozen veil of these icy moons is not just a scientific endeavor, but a journey into the unknown, pushing the boundaries of our understanding of life in the universe. The dance of ice and water, a delicate balance. Beneath the icy surfaces of certain moons in our solar system, a captivating interplay occurs between ice and water, creating environments that might harbor life. This dance is particularly evident on Europa, one of Jupiter's largest moons. Europa's surface is a vast, frozen expanse, but beneath it lies a subsurface ocean, kept liquid by tidal forces from Jupiter's gravity. The ice shell above is not static, it fractures and shifts, allowing water to occasionally erupt in plumes that reach space. This dynamic interplay suggests a complex system where ice and water constantly exchange materials, potentially creating niches for life to take hold. The balance between ice and water on Europa is delicate, maintained by a combination of internal heat and the moon's interaction with Jupiter. The gravitational pull from the gas giant causes Europa to flex, generating heat through friction. This heat prevents the subsurface ocean from freezing solid, while the ice shell above insulates it from the extreme cold of space. The ice shell itself is not uniform. It varies in thickness, with some areas potentially being thin enough to allow sunlight to penetrate, providing energy for potential life forms. The interplay between these factors creates a unique environment where life, as we know it, could theoretically exist. Scientists study these icy moons using a variety of methods, from spacecraft observations to computer models. For instance, the Galileo mission provided valuable data about Europa's magnetic field, which hinted at the presence of a subsurface ocean. More recently, the Hubble Space Telescope has captured images of water vapor plumes erupting from Europa's surface, further supporting the idea of a dynamic interplay between ice and water. These observations are crucial for understanding the potential habitability of these worlds. The dance of ice and water on Europa and similar moons offers a tantalizing glimpse into the possibilities of life beyond Earth, hidden beneath icy surfaces. Cassini's glimpse, Enceladus's icy secrets. Beneath the icy crust of Enceladus, Saturn's sixth largest moon, a hidden ocean of liquid water might be harboring life. The Cassini spacecraft, which orbited Saturn from 1997 to 2017, provided tantalizing evidence of this subsurface ocean. It captured images of geysers erupting from the moon's south polar region, spewing water vapor and ice particles into space. These geysers, known as cryovolcanoes, suggested that Enceladus has a source of internal heat, possibly due to tidal forces exerted by Saturn's gravity. This heat could keep the subsurface ocean liquid, creating a potential habitat for life. The composition of the plumes ejected by Enceladus has been a subject of intense study. Cassini's instruments detected complex organic molecules in these plumes, including nitrogen and oxygen-bearing compounds. These molecules are essential building blocks of life as we know it. Moreover, the presence of hydrogen in the plumes hinted at hydrothermal activity on the ocean floor. On Earth, hydrothermal vents support diverse ecosystems, raising the possibility that similar life forms might exist on Enceladus. Enceladus is not alone in its potential to host life. Europa, one of Jupiter's moons, is another icy world with a subsurface ocean. Like Enceladus, Europa's surface is covered with a layer of ice, but beneath it lies a global ocean of liquid water. The Galileo spacecraft, which studied Jupiter and its moons from 1995 to 2003, provided evidence of this ocean. It detected a magnetic field around Europa that varied in strength, suggesting the presence of a conductive layer, likely a salty ocean, beneath the ice. The Hubble Space Telescope has also observed water vapor plumes erupting from Europa's surface, similar to those seen on Enceladus. The study of subsurface oceans on icy moons like Enceladus and Europa is a rapidly evolving field. Scientists are developing new technologies and missions to explore these distant worlds. For instance, NASA's Europa Clipper mission, set to launch in the coming years, will conduct detailed investigations of Europa's ice shell, ocean, and active geology. Similarly, the Enceladus orbolander concept, a proposed mission, would orbit and eventually land on Enceladus to study its habitability. These missions could provide groundbreaking insights into the potential for life beyond Earth. Jupiter's moon, Europa's hidden depths. Beneath the icy surface of Europa, one of Jupiter's moons, lies a tantalizing possibility, a vast, hidden ocean that could potentially harbor life. This moon, slightly smaller than Earth's own moon, is covered in a thick layer of ice, but evidence from various spacecraft missions, particularly the Galileo mission, suggests that beneath this frozen crust, there is a global ocean of liquid water. The presence of this subsurface ocean is inferred from several lines of evidence, including the moon's relatively young and smooth surface, which suggests ongoing geological activity, and the presence of a magnetic field that is likely generated by the movement of conductive fluid, such as salty water, beneath the surface. The conditions within Europa's subsurface ocean are of great interest to astrobiologists. The ocean is likely in contact with a rocky seafloor, providing essential minerals and nutrients that could support life. Additionally, tidal forces exerted by Jupiter's immense gravity could generate hydrothermal vents on the ocean floor, similar to those found in Earth's oceans. These vents are known to support diverse and thriving ecosystems on Earth, even in the absence of sunlight. The combination of liquid water, essential chemicals, and potential energy sources makes Europa's subsurface ocean a prime candidate in the search for extraterrestrial life. Scientists are particularly excited about the possibility of microbial life forms thriving in Europa's hidden depths. On Earth, microorganisms have been found in some of the most extreme environments, from the depths of the ocean to the heart of volcanoes. If life can exist in such harsh conditions on Earth, it is plausible that similar life forms could exist in Europa's subsurface ocean. To explore this possibility, future missions are being planned to study Europa up close. NASA's Europa Clipper mission, set to launch in the 2020s, will perform detailed reconnaissance of the Moon, including high-resolution imaging and extensive measurements of the Moon's magnetic field and subsurface ocean. This mission could pave the way for a future lander that would directly sample the Moon's surface and potentially even its subsurface ocean. The study of Europa's hidden depths is not just about the search for life. It also provides valuable insights into the processes that shape icy moons and their potential habitability. Understanding the dynamics of Europa's subsurface ocean can help scientists better comprehend the conditions necessary for life to arise and thrive in the cold, dark environments found throughout the outer solar system. Moreover, the exploration of Europa serves as a testament to human curiosity and our relentless pursuit of knowledge, driving us to explore the farthest reaches of our solar system in the hope of answering one of humanity's most profound questions: are we alone in the universe? The tantalizing promise of Ganymede. Ganymede, Jupiter's largest moon, is a celestial body that has captivated scientists with its potential to harbor life. Beneath its icy surface, there's strong evidence suggesting the presence of a subsurface ocean. This ocean is likely sandwiched between layers of ice, with the outer layer being frozen and the inner one potentially liquid due to tidal heating caused by Jupiter's immense gravitational pull. The existence of this hidden ocean makes Ganymede a prime candidate in the search for extraterrestrial life. The icy moon shares similarities with Europa, another of Jupiter's moons, which is also believed to have a subsurface ocean. However, Ganymede's ocean is thought to be much larger and potentially more stable. Scientists have used data from the Galileo spacecraft and the Hubble Space Telescope to study Ganymede's magnetic field and auroras, which provide clues about the moon's internal structure. The presence of a magnetic field suggests the existence of a conductive, salty ocean beneath the ice, further fueling speculation about the possibility of life. Subsurface ocean science is a rapidly evolving field, with Ganymede at the forefront of research. The moon's unique characteristics, such as its magnetic field and the potential for chemical interactions between the ocean and the rocky seafloor, create an environment that could support life. On Earth, life thrives in extreme environments, such as deep-sea hydrothermal vents, where sunlight doesn't reach. Similar conditions might exist in Ganymede's hidden ocean, making it a tantalizing target for future exploration. To uncover the secrets of Ganymede's subsurface ocean, scientists are developing advanced technologies and mission concepts. The European Space Agency's Jupiter Icy Moons Explorer (JUICE) mission, set to launch in the near future, will perform detailed investigations of Jupiter and its icy moons, including Ganymede. The mission aims to characterize the ocean, study the moon's magnetic field, and assess the habitability of this enigmatic world. With each new discovery, Ganymede's promise as an ocean world grows, bringing us one step closer to answering the age-old question: are we alone in the universe? Callisto, a quiet contender in the search for life. Callisto, one of Jupiter's largest moons, often plays second fiddle to its more famous sibling, Europa, in the quest for extraterrestrial life. Yet, this quiet contender harbors secrets that could make it a prime candidate for hosting life beneath its icy surface. Unlike Europa, which experiences intense tidal forces from Jupiter, Callisto orbits further out, leading to a more stable environment. This stability might allow for a subsurface ocean that has remained liquid for billions of years, providing a potential haven for life. The science behind subsurface oceans on icy moons like Callisto is fascinating. These oceans are believed to be kept liquid by a combination of internal heat and the insulating properties of the overlying ice. On Callisto, the lack of significant tidal heating means that any subsurface ocean would rely more heavily on radiogenic heating, heat generated by the decay of radioactive elements within the moon's rocky core. This process could create a thick layer of liquid water, possibly sandwiched between layers of ice. The exact depth and composition of this ocean remain unknown, but recent models suggest it could be substantial. Comparisons with Europa offer valuable insights. Europa's ocean is thought to be in direct contact with its rocky mantle, providing a rich source of minerals and energy that could support life. Callisto, however, might have a more complex structure. Its ocean could be separated from the rocky core by a layer of high-pressure ice, which would limit the exchange of chemicals but might also create unique chemical environments. These differences make Callisto an intriguing case study in the search for life, as they highlight the diverse conditions that could exist on icy moons. The search for life on Callisto is still in its early stages, but the potential is undeniable. Future missions, such as NASA's proposed Jupiter Icy Moons Explorer (JUICE), could provide crucial data about Callisto's interior. By studying the moon's magnetic field, gravity, and surface features, scientists hope to uncover more about its subsurface ocean and the possibility of life. Until then, Callisto remains a quiet contender, waiting in the shadows of its more celebrated neighbors, but no less deserving of our attention. Titan's methane lakes, a different kind of ocean world. Beneath its thick, hazy atmosphere, Saturn's moon Titan hides a landscape both alien and eerily familiar. Rivers etch their paths through mountains, collecting in vast lakes and seas. But unlike Earth's water bodies, these are filled with methane and ethane, hydrocarbons that exist as gases on our planet. Titan's lakes are a testament to the moon's frigid temperatures, where water ice is as hard as rock, and these complex hydrocarbons flow like water, creating a cycle that mirrors Earth's hydrological one. This makes Titan one of the most Earth-like worlds in the solar system, yet profoundly different. The lakes of Titan are scattered around its poles, with the largest, Krakenmeer, spanning an area larger than Earth's Caspian Sea. These bodies of liquid are fed by methane rain, which falls from the sky and carves gullies and channels into the icy terrain. Beneath the surface, scientists suspect there might be a subsurface ocean of liquid water, much like those suspected to exist on Europa and Enceladus. This hidden ocean, if it exists, could harbor conditions suitable for life, shielded from the harsh radiation and extreme cold of the surface. The lakes themselves, while not water-based, might also harbor exotic forms of life adapted to a methane-rich environment. Titan's lakes are not just bodies of liquid. They are dynamic systems that interact with the moon's atmosphere and surface. Sunlight causes the hydrocarbons in the lakes to evaporate, forming clouds that eventually precipitate back down as methane rain. This cycle is driven by seasonal changes, with the lakes growing and shrinking in response to Titan's long, slow orbit around Saturn. The lakes also interact with the icy bedrock, dissolving and depositing minerals in a process that might create unique chemical environments. These interactions make Titan's lakes a fascinating subject for astrobiologists, who are eager to explore their potential for hosting life. The study of Titan's lakes is still in its infancy, with much left to learn. Future missions, like NASA's Dragonfly, aim to explore Titan's surface and atmosphere in greater detail. Dragonfly, a robotic rotorcraft, will sample the surface and atmosphere at various locations, studying the moon's chemistry and habitability. It will also search for signs of past or present life, focusing on the complex organic chemistry that might lead to life's emergence. While Titan's lakes are not water-based, they offer a unique opportunity to study a different kind of ocean world, one that challenges our Earth-centric views of life and habitability. The Ceres Enigma, dwarf planet with subsurface secrets. Ceres, the largest object in the asteroid belt, has long been a subject of fascination for astronomers. Its status as a dwarf planet is just the beginning of its intrigue. Beneath its icy surface, scientists suspect a hidden ocean might exist, adding Ceres to the growing list of celestial bodies that could potentially harbor life. This suspicion is fueled by observations from NASA's Dawn mission, which revealed bright spots in the Enceladus crater, likely composed of sodium carbonate deposits. These deposits suggest the presence of briny water or liquid beneath the surface, a tantalizing clue for astrobiologists. The idea of subsurface oceans is not new. Europa, one of Jupiter's moons, has been a prime candidate for hosting such an ocean. Its icy surface and the presence of a magnetic field indicate a global ocean beneath. Ceres, however, offers a different perspective. Unlike Europa, Ceres is not a moon but a dwarf planet, and its smaller size and different composition provide unique conditions. The subsurface ocean on Ceres, if it exists, would be much smaller and potentially more isolated. Yet, the presence of water, even in small quantities, raises the possibility of microbial life. Understanding these subsurface oceans requires advanced scientific tools and missions. The Dawn mission has been instrumental in gathering data about Ceres. It has provided high-resolution images and spectral data that hint at the composition of the dwarf planet's surface. Scientists are now looking for ways to probe deeper, perhaps with future missions that can drill through the icy crust. The technology to do this is still in development, but the potential payoff is immense. Discovering life, even in its simplest form, would be a groundbreaking achievement. The study of Ceres and other icy worlds is part of a broader effort to understand the potential for life beyond Earth. Europa, Enceladus, and other moons have shown that subsurface oceans are not uncommon in our solar system. Each of these worlds offers a different set of conditions, providing a diverse range of environments to study. Ceres, with its unique characteristics, adds another piece to this puzzle. The search for life is not just about finding extraterrestrial beings. It's about understanding the conditions that make life possible. Every discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Pluto's heart, a possible hidden ocean. Pluto, once considered a mere icy rock at the edge of our solar system, has revealed itself to be a world of surprises. Among its most intriguing features is the heart-shaped glacier named Tombaugh Regio, which may harbor a hidden ocean beneath its icy surface. This possibility has sparked considerable interest among scientists, as it adds Pluto to the growing list of celestial bodies that could potentially support life. The heart-shaped region is composed of nitrogen and methane ices, with a vast, smooth plain known as Sputnik planitia. This plain is unusually devoid of craters, suggesting it is geologically young and active. Such activity could be driven by a subsurface ocean, which might also explain the unusual alignment of Pluto's heart with its tidal axis. The idea of a hidden ocean on Pluto is not as far-fetched as it once seemed. Similar bodies, like Jupiter's moon Europa and Saturn's moon Enceladus, are known to have subsurface oceans beneath their icy crusts. These oceans are kept liquid by tidal heating, a process where gravitational forces from the parent planet stretch and compress the moon, generating heat. On Europa, this has led to a global ocean beneath its ice shell, while Enceladus spews water vapor and ice particles from its south polar region, indicating a subsurface reservoir. Pluto, though much smaller, could experience similar processes. The dwarf planet's eccentric orbit and interactions with its largest moon, Charon, might generate enough tidal heating to maintain a liquid ocean beneath its heart-shaped glacier. Scientists are particularly interested in the potential for life in these subsurface oceans. On Earth, life thrives in extreme environments, from deep-sea hydrothermal vents to subglacial lakes. If similar conditions exist in Pluto's hidden ocean, it's possible that life could have emerged there as well. The necessary ingredients for life as we know it, water, energy, and certain chemical elements, could all be present. However, the extreme cold, darkness, and high pressure of such an environment would pose significant challenges. Nevertheless, the discovery of life in these harsh conditions would have profound implications for our understanding of life's potential throughout the universe. To better understand Pluto's heart and its potential hidden ocean, scientists rely on data from the New Horizons spacecraft, which performed a flyby of Pluto in 2015. The spacecraft's images and measurements have provided valuable insights into the dwarf planet's geology, composition, and atmosphere. Future missions could further explore Pluto and other icy worlds, using advanced instruments to probe beneath their surfaces. Until then, the heart-shaped glacier on Pluto remains a tantalizing enigma, a possible harbor for life in the cold, dark depths of our solar system. The science of ice shells, thickness, and composition. Beneath the icy surfaces of certain moons in our solar system, scientists suspect that vast oceans might harbor life. These ice-covered worlds, like Europa, one of Jupiter's moons, present a fascinating enigma. The ice shells encasing these subsurface oceans vary significantly in thickness and composition, playing a crucial role in understanding the potential habitability of these environments. Europa's ice shell, for instance, is estimated to be between 15 to 25 kilometers thick. This might seem like an impenetrable barrier, but it's not necessarily a dead end for life. Beneath this icy crust, a global ocean of liquid water is believed to exist, kept warm by tidal forces exerted by Jupiter's immense gravity. The composition of Europa's ice shell is also intriguing. It's not pure water ice, but contains various impurities, such as salts and possibly organic materials, which could provide the necessary ingredients for life. The thickness and composition of ice shells on these ocean worlds are critical factors in assessing their potential to support life. Thicker ice shells might insulate the subsurface oceans from harmful radiation, while also posing a challenge for any potential life forms to access energy and nutrients from the surface. On the other hand, thinner ice shells might allow for more exchange between the surface and the ocean, but could also expose the ocean to more radiation. The composition of the ice can also influence the chemistry of the subsurface ocean, potentially providing the necessary elements for life. Scientists are using a variety of methods to study these ice shells, including remote sensing from spacecraft and computer modeling. By analyzing the data, they can infer the thickness and composition of the ice and gain insights into the conditions within the subsurface oceans. For example, the presence of certain minerals or organic compounds on the surface could hint at similar materials within the ice shell or even the ocean itself. This information is vital for planning future missions that might one day directly explore these icy moons and their hidden oceans. Cracks and plumes, windows into subsurface oceans. Beneath the icy surfaces of some of our solar system's moons, scientists suspect hidden oceans might exist, shielded from the harsh vacuum of space. Europa, one of Jupiter's largest moons, is a prime candidate. Its surface is a vast, cracked expanse of ice, hinting at the dynamic processes beneath. These cracks, some stretching for thousands of kilometers, are more than just surface features. They are windows into a potential subsurface ocean, offering tantalizing clues about what might lie hidden beneath. Plumes of water vapor have been observed erupting from Europa's surface, further fueling speculation about a subsurface ocean. These plumes, detected by the Hubble Space Telescope, provide a direct sample of the moon's interior, potentially carrying water and other materials from the hidden ocean to the surface. Analyzing these plumes could reveal the composition of the subsurface ocean and even provide insights into the possibility of life. The plumes are not just spectacular displays. They are scientific gold mines, offering a glimpse into an otherwise inaccessible world. The study of these cracks and plumes is not just about understanding Europa. It's about uncovering the potential for life in the most unexpected places. Subsurface oceans, shielded from radiation and extreme temperatures, could provide stable environments for life to thrive. On Earth, life has been found in similar extreme environments, such as deep-sea hydrothermal vents. If similar conditions exist in Europa's subsurface ocean, life might have found a way to exist there as well. The cracks and plumes are our best chance to peer into these hidden worlds and uncover their secrets. Chemical energy, the fuel for potential life. Beneath the icy surfaces of some of our solar system's moons, there's a tantalizing possibility: hidden oceans that could harbor life. These ocean worlds, like Europa, one of Jupiter's moons, are enshrouded in thick layers of ice, but evidence suggests that liquid water might exist beneath. Where there's liquid water, there's potential for life, and the energy source for that life could be chemical energy. On Earth, chemical energy fuels life in extreme environments, and similar processes might be at play in these distant, icy worlds. Chemical energy is a fundamental driver of life as we know it. In the absence of sunlight, which is the primary energy source for life on Earth's surface, organisms can harness energy from chemical reactions. This is how life thrives in Earth's deep-sea hydrothermal vents, where sunlight doesn't reach. Similarly, if life exists in the subsurface oceans of Europa or other icy moons, it would likely rely on chemical energy. The process of chemosynthesis, where organisms convert chemical energy into biological energy, could be the key to life's survival in these harsh, lightless environments. The science of subsurface oceans is still in its infancy, but it's a rapidly evolving field. Europa's ocean, for instance, is believed to be in contact with its rocky core, creating a dynamic environment rich in minerals and chemical compounds. These interactions could produce a variety of chemical energy sources, such as hydrogen and sulfur compounds, which could support life. Moreover, recent studies have shown that the icy shells of these moons might be more dynamic than previously thought, with potential exchanges between the surface and the subsurface ocean. This could provide additional avenues for chemical energy to fuel potential life forms. The search for life in these ocean worlds is not just about finding extraterrestrial beings. It's about understanding the limits of life and the conditions under which it can thrive. By studying these icy moons, scientists hope to uncover the secrets of life's resilience and adaptability. The quest for chemical energy sources in these subsurface oceans is a crucial part of this exploration. It's a journey that takes us to the far reaches of our solar system, peeling back the icy layers to reveal the hidden potential for life. Hydrothermal vents, oases of life on Earth and beyond. Deep beneath the waves, where sunlight never reaches, hydrothermal vents create oases of life in the most inhospitable corners of our planet. These vents, often found near underwater volcanoes, spew scorching, mineral-rich water into the frigid ocean depths. Surprisingly, they support thriving ecosystems teeming with unique organisms. Tube worms, giant clams, and blind shrimp cluster around these vents, sustained by chemosynthetic bacteria that convert toxic chemicals into energy. This discovery has revolutionized our understanding of life's adaptability and resilience. The existence of these vibrant ecosystems has sparked intriguing questions about the potential for life beyond Earth. Icy moons like Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are thought to harbor subsurface oceans beneath their frozen surfaces. These oceans, warmed by tidal forces and possibly hydrothermal activity, could provide the necessary ingredients for life. Scientists speculate that if life can thrive near hydrothermal vents on Earth, it might also find a foothold in similar environments elsewhere in the solar system. The exploration of these icy moons is a top priority for astrobiologists seeking to answer one of humanity's most profound questions: are we alone in the universe? Subsurface ocean science is a burgeoning field driven by advancements in technology and our growing understanding of planetary bodies. Robotic explorers, like NASA's Europa Clipper mission, aim to study the icy moon's subsurface ocean and search for signs of habitability. Meanwhile, Earth-based research continues to uncover new species and ecosystems around hydrothermal vents, expanding our knowledge of life's limits. The interplay between these two areas of study is crucial. Each discovery on Earth informs our understanding of potential extraterrestrial life, and each mission to an icy moon broadens our perspective on the possibilities of life in the cosmos. This synergy drives the quest to find life beyond our planet, making the study of hydrothermal vents and subsurface oceans more exciting than ever. The role of tides, a cosmic mixing pot. Beneath the icy surfaces of some of our solar system's moons, vast oceans hide, shielded from the harshness of space. These ocean worlds, like Europa, one of Jupiter's largest moons, have captivated scientists for decades. The tides, driven by the gravitational pull of their parent planets, play a pivotal role in these hidden seas. They are not just the ebb and flow of water, but a cosmic mixing pot, stirring up the subsurface oceans and potentially creating environments conducive to life. Tides on these icy moons are vastly different from those on Earth. The immense gravitational forces exerted by Jupiter on Europa, for instance, cause the moon's icy shell to flex and bend. This constant deformation generates heat through tidal friction, which could be enough to keep the subsurface ocean liquid. Moreover, these tidal forces also drive the movement of water within the ocean, creating currents and mixing different layers. This mixing is crucial as it can distribute nutrients and energy sources, which are essential for life as we know it. The subsurface ocean science is a burgeoning field, with researchers using sophisticated models and data from missions like NASA's Galileo and the upcoming Europa Clipper. These studies aim to understand the dynamics of these hidden seas better. For instance, the interaction between the ocean and the icy shell above is a critical area of research. Tidal forces can cause cracks and fissures in the ice, allowing water to exchange between the ocean and the surface. This exchange could potentially deposit vital chemicals from the surface, like those from meteorites or outgassed materials, into the ocean, providing a feast for any potential life forms. Furthermore, the tides can also influence the ocean's chemistry. The mixing can expose different water layers to various pressures and temperatures, facilitating a range of chemical reactions. Some of these reactions could lead to the formation of complex organic molecules, the building blocks of life. For example, hydrothermal vents on Earth's ocean floors support diverse ecosystems by providing a mix of chemicals and energy. Similar processes could be happening in the subsurface oceans of Europa and other icy moons, offering a tantalizing possibility for extraterrestrial life. Extremophiles, Earth's resilient life forms. In the harshest environments on Earth, where temperatures plunge, pressures soar, and conditions seem inhospitable to life as we know it, extremophiles thrive. These resilient organisms, ranging from bacteria to multicellular animals, have evolved to survive and even flourish in extreme conditions. They inhabit places like deep-sea hydrothermal vents, acidic hot springs, and the Antarctic ice shelves. Their existence challenges our understanding of life's limits and opens up intriguing possibilities for life beyond Earth, particularly in the icy moons of our solar system. Take, for instance, the tardigrade, often dubbed the water bear. This microscopic creature can survive extreme dehydration, radiation, and temperatures ranging from -300 degrees Fahrenheit to 300 degrees Fahrenheit. Similarly, certain species of archaea, a domain of single-celled organisms, have been found in the boiling waters of Yellowstone's hot springs and the frigid brines of Antarctica. These extremophiles have developed unique adaptations, such as heat shock proteins and antifreeze proteins, to cope with their extreme environments. Their resilience suggests that life might find a way to persist in the subsurface oceans of icy moons like Europa, where conditions are far from the cozy comforts of Earth's surface. The study of extremophiles has significant implications for astrobiology, the science of searching for life beyond Earth. Europa, one of Jupiter's moons, is a prime candidate in this search. Beneath its icy surface, scientists believe there lies a global ocean of liquid water, kept warm by tidal forces exerted by Jupiter's gravity. This subsurface ocean could harbor conditions suitable for life, much like the extreme environments on Earth where extremophiles thrive. To explore this possibility, missions like NASA's Europa Clipper are being planned to study the moon's ice shell, ocean, and geology. Understanding extremophiles on Earth not only broadens our knowledge of life's adaptability, but also guides our search for life in the cosmos. Moreover, the study of extremophiles has practical applications on Earth. For instance, enzymes from extremophiles are used in various industries, from biofuels to medicine. These enzymes, stable under extreme conditions, can catalyze reactions that are otherwise difficult to achieve. Furthermore, extremophiles can help us understand how life might adapt to climate change, as some of these organisms are already thriving in environments that mimic future climate scenarios. In essence, extremophiles are not just fascinating life forms. They are also valuable allies in our quest to understand and adapt to a changing world. The search for biosignatures. What to look for? In the cold, dark expanses of our outer solar system, beneath the icy surfaces of moons like Europa, Ganymede, and Enceladus, scientists suspect that vast oceans of liquid water might harbor life. These subsurface oceans, kept liquid by tidal heating and the insulating properties of ice, present a tantalizing prospect for astrobiologists. The search for biosignatures in these ocean worlds focuses on detecting signs of life that might be hidden beneath the ice. Biosignatures can be any substance, like an element, molecule, or even a particular pattern that indicates the presence of life. They could be direct evidence, such as microbial fossils or organic molecules, or indirect evidence, like specific atmospheric gases that life might produce. One of the most promising biosignatures to look for is molecular oxygen. On Earth, oxygen is a clear indicator of life, as it is a byproduct of photosynthesis. However, detecting oxygen in the atmospheres of icy moons is challenging. Europa, for instance, has a tenuous atmosphere that contains trace amounts of oxygen, but it's unclear whether this oxygen is produced by life or by other processes, such as radiolysis, where radiation splits water molecules into hydrogen and oxygen. Scientists are also interested in other gases, like methane, which can be produced by both geological and biological processes. The key is to look for an imbalance or an unusual abundance of these gases, which could hint at life. Another approach is to look for organic molecules, the building blocks of life as we know it. These molecules can be detected in the ice or in plumes of water vapor that erupt from the subsurface oceans. Enceladus, for example, has geysers that spew water vapor and ice particles into space, some of which contain organic molecules. While these molecules can be created abiotically, their presence is a necessary precursor for life. Moreover, complex organic molecules, like amino acids, are strong indicators of life. Scientists are also interested in looking for specific patterns or structures in these molecules that could indicate a biological origin. In addition to chemical biosignatures, scientists are also exploring the possibility of detecting life through its physical traces. For instance, life can alter the mineralogy of its surroundings, leaving behind distinctive patterns or structures. On Earth, certain types of microbes can create stromatolites, which are layered structures formed by the trapping, binding, and cementation of sedimentary grains by biofilms of microorganisms. If similar structures were found on an icy moon, it could be a strong indication of life. Furthermore, life can also leave behind isotopic signatures or specific ratios of different isotopes of an element, which can be detected through careful analysis. These isotopic signatures can provide clues about the origin and evolution of life, as well as its current state. Microbial mats, the simplest forms of life. Beneath the icy surfaces of some of our solar system's most intriguing moons, like Europa and Enceladus, scientists speculate that life might find a way to thrive. These ocean worlds harbor vast subsurface oceans, kept liquid by tidal forces and potentially hydrothermal vents. In such extreme environments, life might take its simplest forms, such as microbial mats. These mats are complex communities of microorganisms that form dense layers, often adhering to surfaces like rocks or the seafloor. On Earth, they are found in diverse environments, from hot springs to the deep sea, showcasing their adaptability and resilience. Microbial mats are structured communities where different types of microbes live together, each playing a role in the mat's overall function. They can include cyanobacteria, which perform photosynthesis, and other bacteria that use chemicals for energy. In the absence of sunlight, as would be the case in subsurface oceans, these mats might rely on chemosynthesis, using chemicals like hydrogen sulfide or methane for energy. This process is similar to what occurs near hydrothermal vents on Earth, where life thrives in the absence of sunlight. The potential for similar processes on icy moons is a tantalizing prospect for astrobiologists. The study of subsurface ocean science is crucial for understanding these potential habitats. On Earth, scientists explore extreme environments like deep-sea vents and subglacial lakes to understand how life might survive in similar conditions on other worlds. For instance, Lake Vostok in Antarctica, hidden beneath miles of ice, provides a glimpse into how life might exist in Europa's subsurface ocean. The discovery of microbial mats in such extreme environments on Earth fuels speculation about their existence elsewhere. These mats could be the simplest forms of life, yet they represent a profound possibility that life, in some form, might be more common in our universe than previously thought. Technological advancements are opening new avenues for exploring these icy moons. Missions like NASA's Europa Clipper and ESA's JUICE, Jupiter Icy Moons Explorer, aim to study these moons in detail, searching for signs of habitability and potentially even life. Instruments designed to detect chemical signatures of life, such as specific minerals or organic compounds, could provide evidence of microbial mats or other life forms. The data collected from these missions will be instrumental in understanding the potential for life in subsurface oceans. Until then, the mystery of what lies beneath the ice remains one of the most compelling questions in astrobiology. The challenges of exploring ocean worlds. Beneath the icy surfaces of certain moons in our solar system, scientists suspect that vast oceans might harbor life. Europa, one of Jupiter's moons, is a prime candidate. It's covered in a thick layer of ice, but data from spacecraft like NASA's Galileo mission suggest a global ocean lies beneath. The challenge? Getting through that ice to explore what's underneath. The ice shell on Europa could be tens of kilometers thick, making it a formidable barrier. Even if we could penetrate it, the extreme cold and pressure pose significant obstacles. Plus, any life down there would likely be microbial, making it hard to detect. Another hurdle is the lack of direct access. We can't just send a submarine down there like we do on Earth. The technology to drill through kilometers of ice in such harsh conditions doesn't exist yet. Even if it did, contamination is a major concern. We need to ensure that any probe we send is sterile to avoid introducing Earth microbes and potentially compromising the scientific integrity of the mission. The ocean worlds are pristine environments, and we have a responsibility to keep them that way. Then there's the issue of energy. On Earth, life in the deep ocean often thrives near hydrothermal vents, where chemical energy is abundant. But on Europa or other icy moons, the energy sources might be different. Life might rely on chemical energy from the interaction of water and rock, or perhaps from energy generated by tidal forces. Understanding these potential energy sources is crucial for knowing where and how to look for life. It's a complex puzzle, and each piece we find brings us closer to understanding the potential for life beyond Earth. Despite these challenges, the scientific community is making strides. Missions like NASA's Europa Clipper, set to launch in the coming years, will conduct detailed reconnaissance of Europa's ice shell and ocean. They'll use advanced instruments to study the moon's composition, geology, and potential habitability. While we may not be ready to drill through the ice just yet, each mission brings us closer to that goal. The search for life in these ocean worlds is a marathon, not a sprint. But with each step, we learn more about our solar system and our place in it. Future missions, our quest to unveil the truth. Beneath the icy crusts of distant moons, scientists believe, lie hidden oceans that could harbor life. Europa, one of Jupiter's largest moons, is a prime candidate. Its surface is a vast, cracked expanse of ice, beneath which lies a global ocean of liquid water. This ocean is kept liquid by tidal forces from Jupiter, which generate heat through friction. The presence of this subsurface ocean makes Europa a tantalizing target for astrobiologists. Similar conditions might exist on other icy moons, such as Ganymede and Callisto, also orbiting Jupiter, and Enceladus, a tiny moon of Saturn. These worlds are not bathed in the warmth of the sun, but they might still harbor life, protected by their icy shells. To explore these ocean worlds, several missions are in the works. NASA's Europa Clipper, set to launch in the coming years, will perform detailed reconnaissance of Europa. It will assess the moon's habitability by studying its ice shell, ocean, and geology. The spacecraft will also look for signs of recent or ongoing geological activity, which could bring material from the subsurface ocean to the surface. Meanwhile, the European Space Agency's JUICE, Jupiter Icy Moons Explorer, mission will study Ganymede, Callisto, and Europa. It aims to understand the conditions that might allow for life in their subsurface oceans. These missions will use a variety of instruments, including cameras, spectrometers, and ice-penetrating radar, to gather data. One of the most exciting aspects of these missions is the potential to directly sample the subsurface oceans. Enceladus, for instance, has geysers that spew water vapor and ice particles into space. Some of these particles contain salts and organic compounds, suggesting that the moon's subsurface ocean is interacting with its rocky core. Future missions could fly through these plumes to collect samples, analyzing them for signs of life. Similarly, Europa's chaotic terrain suggests that its ice shell is dynamic, with material from the subsurface ocean occasionally breaking through to the surface. A lander mission could potentially sample this material directly. These efforts represent a significant step forward in our quest to uncover the truth about life beyond Earth. The technology needed to pierce the ice. Beneath the icy surfaces of some of our solar system's moons, scientists suspect there could be hidden oceans, potentially harboring life. Europa, one of Jupiter's moons, is a prime candidate. Its ice shell is thought to be 1525 kilometers thick, with a subsurface ocean that could be up to 100 kilometers deep. To explore these tantalizing environments, researchers need innovative technology to pierce the ice and access the water below. One of the main challenges is developing a system that can melt or drill through the ice without contaminating the subsurface ocean. Traditional drilling methods used on Earth are not suitable for these icy moons. Instead, scientists are exploring alternative approaches. For instance, the use of heated probes or nuclear-powered melt probes could be viable options. These probes would slowly melt the ice as they descend, creating a narrow tunnel to the ocean below. The heat generated would also help sterilize the probe, reducing the risk of contaminating the pristine environment. Another critical aspect is ensuring that the technology can withstand the extreme conditions. The ice shells of these moons are not only thick, but also incredibly cold, with temperatures plummeting to minus 140 degrees Celsius. Additionally, the radiation environment around Jupiter is intense, posing further challenges for any electronic equipment. To tackle these issues, researchers are developing robust, radiation-hardened electronics and materials that can operate in such harsh conditions. For example, silicon-germanium alloys are being considered for their ability to function at low temperatures and resist radiation damage. Moreover, the technology must be capable of collecting and analyzing samples in situ. Once the probe reaches the subsurface ocean, it needs to be equipped with instruments to detect signs of life, such as specific chemicals or microorganisms. Advanced sensors, spectrometers, and even small, autonomous underwater vehicles are being considered for this purpose. These tools would allow scientists to explore the ocean and gather data without the need for immediate human intervention. The data collected could provide valuable insights into the potential habitability of these icy worlds and the possibility of extraterrestrial life. Robotic explorers, the next frontier in space exploration. Beneath the icy surfaces of distant moons, a tantalizing possibility exists: hidden oceans that could harbor life. Europa, one of Jupiter's largest moons, is a prime candidate. It's covered in a thick layer of ice, but beneath that frozen crust, scientists strongly suspect a global ocean of liquid water. This ocean is kept liquid by tidal forces from Jupiter, which generate heat through a process called tidal flexing. The potential for liquid water is exciting because, as far as we know, life needs it. But how do we explore such a distant, inhospitable place? Enter robotic explorers, the next frontier in space exploration. These robotic pioneers are designed to withstand extreme conditions. They must survive intense radiation, frigid temperatures, and the mechanical challenges of operating in an alien environment. One concept is the Europa Clipper, a spacecraft designed to orbit Jupiter and make multiple close flybys of Europa. It will carry a suite of scientific instruments to study the moon's ice shell, ocean, and geology. Another idea is the Europa Lander, a proposed mission that would touch down on the surface and potentially drill through the ice to search for signs of life. These robots are not just tools. They are ambassadors of human curiosity, venturing where we cannot yet go. The science of subsurface oceans is complex and fascinating. On Europa, the ocean is thought to be in direct contact with a rocky seafloor, which could provide essential chemicals for life. Hydrothermal vents on Earth's ocean floor support thriving ecosystems, suggesting that similar processes could occur on Europa. Robotic explorers will analyze the composition of the ice and search for organic molecules, which are the building blocks of life. They will also study the moon's magnetic field, which can provide clues about the ocean's depth, salinity, and potential habitability. Each discovery brings us one step closer to answering the profound question, are we alone in the universe? But the challenges are immense. Drilling through Europa's ice shell, which could be tens of kilometers thick, is a daunting task. Engineers are developing innovative solutions, such as nuclear-powered melt probes that can slowly descend through the ice. These probes would carry scientific instruments to sample the water and analyze its contents. Another challenge is the radiation environment around Jupiter, which can damage electronic systems. Robotic explorers must be hardened against these effects to function effectively. Despite these hurdles, the potential rewards are immense. The search for life beyond Earth is one of the most compelling adventures of our time, and robotic explorers are at the forefront of this quest. The ethical dilemma: contamination and conservation. Beneath the icy crusts of distant moons, oceans of liquid water might harbor life. Europa, one of Jupiter's moons, is a prime candidate. It's believed to have a global ocean beneath its ice shell, kept liquid by tidal heating from Jupiter's gravity. This subsurface ocean could be up to 100 kilometers deep, making it one of the most promising places to look for extraterrestrial life in our solar system. But with this promise comes a dilemma. How do we explore these worlds without contaminating them? And how do we conserve them for future study and potential human benefit? The risk of contamination is real and significant. Earth is teeming with microbial life, and even the cleanest spacecraft could carry thousands of microbes. If these microbes were to hitch a ride to Europa or other icy moons and contaminate their oceans, it could jeopardize scientific research and potentially harm any native life forms. It's a delicate balance. We must protect these environments while also learning as much as we can about them. This is where the concept of planetary protection comes into play. It's a set of guidelines designed to prevent contamination of other celestial bodies by Earth microbes and vice versa. Conservation is another critical aspect. These subsurface oceans are unique and irreplaceable. Once contaminated, they could be altered forever. This is why scientists and engineers are working hard to develop technologies that minimize the risk of contamination. For instance, they're exploring the use of autonomous underwater vehicles that could be sterilized before launch. They're also looking at ways to design missions that minimize contact with the ocean, such as using ice-penetrating radar to study the ocean from a distance. But even with these precautions, there's always a risk. It's a challenge that requires careful consideration and ethical decision-making. Moreover, the ethical dilemma extends beyond scientific research. There's also the question of resource exploitation. If these subsurface oceans contain valuable resources, who has the right to them? How can we ensure that their exploitation doesn't harm potential life forms or the environment? These are complex questions that don't have easy answers, but they're questions we must grapple with as we venture further into the cosmos. After all, our actions today could have profound implications for the future of these icy worlds and the life that might call them home. The philosophical implications: are we alone? Beneath the icy crusts of distant moons, hidden oceans stir, whispering secrets about the potential for life beyond Earth. Europa, one of Jupiter's largest moons, is a prime example. Its surface is a vast, frozen expanse, but beneath lies an ocean of liquid water, possibly twice the volume of Earth's oceans. This subsurface ocean is kept liquid by tidal forces from Jupiter, generating heat through friction. Similar conditions might exist on other icy moons like Enceladus, Saturn's geologically active moon, which spews water vapor and ice particles into space, hinting at a subsurface ocean. The presence of liquid water is a tantalizing clue, but it's not the only ingredient for life. Scientists also look for chemical energy sources and the right mix of elements. On Earth, life thrives near hydrothermal vents, where chemicals from the Earth's interior mix with seawater, creating a rich soup of nutrients. Similar processes could be happening on Europa or Enceladus. If so, life might not need sunlight to exist. It could rely on chemosynthesis, using chemical energy to create organic compounds. This shifts our understanding of habitable zones, expanding the possibilities for life in the universe. Yet, the question remains, are we alone? The discovery of life, even microbial, in these icy oceans would have profound philosophical implications. It would mean that life is not unique to Earth, that it can arise independently in different environments. This would challenge our anthropocentric view of the universe, forcing us to reconsider our place in the cosmos. It might also inspire a sense of unity, showing that life, in some form, is a universal phenomenon. Conversely, if we find no signs of life, it could mean that life is rare, that Earth is a special place. Either way, the search for life in these ocean worlds is a journey of self-discovery, a quest to understand not just the universe, but ourselves. The search for life in these icy oceans is not just a scientific endeavor, it's a philosophical one. It pushes the boundaries of our knowledge and challenges our assumptions. It's a reminder that the universe is vast and full of possibilities. Whether we find life or not, the journey itself is transformative, reshaping our understanding of life, the universe, and our place within it. So, as we explore these ocean worlds, we're not just looking for life. We're looking for answers to some of the most profound questions of our existence. The thrill of discovery, what lies ahead? Beneath the icy crusts of distant moons, a tantalizing possibility lingers: subsurface oceans that could harbor life. Europa, one of Jupiter's largest moons, is a prime candidate. It's covered in a thick layer of ice, but beneath that frozen surface, scientists strongly suspect a global ocean of liquid water. This ocean is kept liquid by tidal forces from Jupiter's gravity, which generate heat through a process called tidal flexing. The presence of this ocean has been inferred from observations made by spacecraft like NASA's Galileo mission, which detected a magnetic field around Europa that's consistent with the presence of a conductive layer, likely a salty ocean. The thrill of discovery lies in the potential to find life in these extreme environments. On Earth, life thrives in even the most inhospitable places, from deep-sea vents to acidic hot springs. If life can adapt to such conditions here, it might also find a way on icy moons. Scientists are particularly interested in Europa's ocean because it may have the necessary ingredients for life: water, energy, and certain chemical building blocks. The moon's ice shell could also act as a protective shield, preserving any potential life from harmful radiation. Exploring these subsurface oceans presents significant challenges. The ice shell on Europa is estimated to be tens of kilometers thick, making direct exploration difficult. However, future missions are being planned to overcome these obstacles. NASA's Europa Clipper mission, set to launch in the coming years, will perform detailed reconnaissance of Europa and investigate whether the icy moon could harbor conditions suitable for life. The mission will also help pave the way for a future lander that could directly study the moon's surface and potentially sample material from the subsurface ocean. The search for life in these icy worlds is not just about finding extraterrestrial organisms. It's about understanding the limits of life and the potential for habitability in the universe. Each discovery brings us one step closer to answering the age-old question: are we alone in the cosmos? The thrill lies in the unknown, in the possibility that we might find life in the most unexpected places, hidden beneath the ice of distant moons. As we conclude our journey into the enigmatic ocean worlds hidden beneath the ice, let's recap the key points that have unfolded before us. We've explored the tantalizing possibilities of life thriving in these alien oceans, where sunlight never reaches, and yet, life might find a way. Europa, with its global ocean beneath its icy crust, stands as a beacon of hope for astrobiologists, offering a tantalizing mix of water, energy, and the essential chemical building blocks of life. We've delved into the cutting-edge science of subsurface ocean exploration, from the tantalizing plumes erupting from Europa's surface to the innovative missions and technologies being developed to pierce the icy veil and explore what lies beneath. The potential for life in these extreme environments is not just a distant dream, but a scientific possibility that drives our curiosity and fuels our exploration. As we look to the future, the mysteries of these ocean worlds beckon us to push the boundaries of our understanding and venture into the unknown. The upcoming Europa Clipper mission, set to launch in the near future, promises to revolutionize our knowledge of this icy moon and its hidden ocean. With each new discovery, we edge closer to answering one of humanity's most profound questions. Are we alone in the universe? So, join us as we continue to explore the wonders of our solar system and beyond. Subscribe to our channel to stay updated on the latest discoveries and missions that will unravel the secrets of these ocean worlds. Together, let's embark on this thrilling journey of exploration and discovery, where the boundaries of life as we know it are redefined and the mysteries of the cosmos are brought to light. The future of space exploration is here, and it's more exciting than ever. Don't miss out. Subscribe now, and let's dive into the unknown together.